Uruguay for some years, and in 2004 she came to Europe. She got a Monica Hall fellowship to work in the Politecnica de Catalunya there. And since last year she is a professor, accreditat. Agregat. She's a professor at the University of Catalunya. Concerning her, well, she did many things with respect to research. She worked in laser systems a lot. She works in numerical modeling, and mainly she worked in neuronal model, excitable system, noise, many different topics, delay effect, many different topics. So she's going to tell us something today also on information theory, and most probably apply to laser, maybe, I don't know. Hopefully. But she's also organizing a conference every year almost.
2 years.
Every 2 years. She has every 2 years a conference in laser, every 2 years a conference in general things of nonlinear dynamics in Uruguay. So if one of you have the chance to go there, I recommend it strongly, because it's a very nice meeting and very well organized, and I always enjoy to be there, so most probably you will enjoy too. So Cristina, thank you very much for coming.
Thanks, Claudio. Thanks everybody for coming here. I want to thank, of course, Claudio and everybody. But Maxi, unfortunately, that's not here. It's a pleasure to be here again, and I hope I don't bore you too much. What I want to try to talk today is about complexity. Let me first show you where I work. I am part of the Dynamics, Optics and Lasers group in Terrassa. I am a member of this group, and this is a quite large group that works basically in two main topics. On one hand, materials, and in my side, photonics, and there's a strong research on biophysics. Here's a list of topics that we work on. Not all of them are in the list, and also it's a very nice place to work. I feel very welcome there, and you're all welcome to visit us. We have a new research building, which is quite nice, and I want to introduce the collaborators. One of them, you know him. He's been here a visitor perhaps last year, I think, Osvaldo. He's originally from Argentina, spent some time in Australia. Now he has moved to spend a few years in Belo Horizonte, in Brazil. Then my collaborators in Terrassa, Jordi Garcia, who's the head of the group in the biophysics part, and Karma has also been here. And over there, in that corner there, Jordi Tiana, who is part of the experimental work. And I'm also going to show some work in progress that's been done in old friends in Uruguay, one Marcelo Barreiro and Arturo Martí. Arturo Martí has also been a visitor here. Marcelo Barreiro is a very good meteorologist. Anyway, so what is the concept of complexity? We can say that a complex system is easy to recognize, but it's hard to quantify the degree of complexity of the system. In particular, we can say in a general way that complexity is characterized by certain signatures of some correlation, some order. This can be either temporal or spatial or both. And what we would like is to have a quantity, called C, that is a measure of complexity in a similar way as Shannon's entropy measures randomness. Or in low-dimensional systems, how Lyapunov exponents can give an idea of how the degree of chaoticity of the system. So let's begin by excluding some things. For instance, this is just a schematic. What do you expect? This is an ordered pattern, has zero entropy, because it's not random at all, and it's not complex. And on the other hand, you have complete disorder, and you have normalized maximum entropy, which is 1, and also zero complexity, and something in between, which in this case is a chaotic pattern, can have some degree of complexity, which is what we're trying to define, and some degree of randomicity also. So to begin with, periodic motion is not complex, and purely random motion is not complex. In between these two states, preferred order, which will be, for example, just a regular crystal, or a complete disorder in the limit of thermodynamics ideal gas, then we can say that we're looking for structures, some memories, some symmetries, patterns, etc. But of course, a useful measure needs to do more than being zero in the two extreme conditions. We need to get some meaningful results. Oh, sorry. I just wanted to present the motivation of this. Is can we have complexity induced by noise? I mean, can a simple system that is not complex by itself can have a complex behavior that is just induced by noise? And how to capture how these signatures of patterns present in a system that is what we're trying to define as a complex system. So let me just very briefly say the outline of the talk. I will, in the introduction, introduce two concepts: the complexity measure and Shannon's entropy is well known. And in the second part of this introduction, I'm going to talk about what is called ordinal patterns, which these two things I will use on the two next parts, which is what I want to do is try to detect this noise-induced order and complexity. We will do that employing these complexity measures and the Shannon entropy, and we will do it to very simple systems. In theory, very simple system, which is the driver bistable system and an excitable model. And then in the second part, I will apply the ordinal patterns methodology that I discussed in the introduction to analyze time series, experimental time series. One is something that perhaps some of you are familiar because you have heard of, the regime of LFX in semiconductor lasers with feedback. The other is inferring the complex network of the global Earth temperature anomalies. Okay, so I'm finally the conclusion. So let me just begin by talking about information measure. What is an information measure? Suppose you have a system that is described by a certain probability distribution that you will have to define somehow. Then, once you have the probability distribution, you can define an information measure, just, for instance, just Shannon entropy, but you can use more sophisticated measures if you want, which are, for instance, Sally's or Renji. Depends on what you want to capture, the measure you use. Shannon's entropy is, of course, extensive, but you can use non-extensive measures. And of course, what it makes sense is try to normalize in order to have entropy equals to 1 in the most disordered situation. The normalization constant depends obviously on which measure you choose. For instance, if you're working with Shannon's entropy, then you normalize over the logarithm of n, which is the maximum entropy, and then the maximum value will be 1. This is just a technical point. Then you can define a second quantity, which is your disequilibrium, which is the distance from your probability distribution to the one that is the equilibrium one. The equilibrium one depends on which entropy you have chosen, right? The equilibrium is the one that maximizes the entropy, but once you have chosen your entropy, you have your equilibrium distribution, and then you can define somehow of a distance. The definition of a distance, this is a meeting, there was a lunchtime. There are many definitions, of course. You can define distance in many ways. Simple definition would be Euclidean, or more sophisticated ones, which give you the distance between how different two probability distributions are. In particular, I will focus on the last, on this one here, because it's scientific. And you already do this one, the Hertz and divergence, is just the symmetric form of the Kullback relative entropy. It's the symmetricized form of this one, so it's symmetric.
An absolute value?
Sorry?
Is it an absolute value?
No, this is the conditional probability. The conditional probability of P given. Again, I don't want to intervene a lot into the details, but these are just distance between two probability distributions, different way to define them. And once you have the two elements, so it's your information measure, which is the normalized entropy. We have used the Shannon one, and you also have your disequilibrium. By making the product of these two, you end up with a function that is the complexity measure that has this property of being equal to 0 in both extreme situations of complete order and complete disorder. In complete order, it goes to 0 because Shannon entropy is 0. In complete disorder, it goes to 0 because the disequilibrium is 0, because your distance to the equilibrium distribution is 0. So basically, this actually defines a family of complexities because it depends on which entropy you choose and which distance you choose. Particularly, there have been two entropies that have been studied quite a lot, two complexity measures which change on the definition of the distance. So this one uses Euclidean and this one uses the symmetric form of the Kullback relative entropy. Anyway, this type of complexity measures can be employed for various things. I just want to put a couple of examples to show you that this is actually useful for some applications. In particular, you can do a diagram of the entropy versus the complexity. And if you do that, you can realize that for the complexity is actually a function of the entropy. So for a given value, you have a range of possible values of the complexity, and here, for instance, these lines indicate the borders, and you can have different type of signals occupying different regions of this diagram. For instance, here is a paper in which my colleagues Osvaldo distinguish different type of noises and chaotic dynamics by plotting and employing these complexity entropy diagrams. And they have been receiving attention on the biological community. In particular, I like this paper right here that says that you can distinguish normal brains and those experiencing cortical thickness, which is associated with this Alzheimer's disease, by analyzing time series and plotting diagrams in the complexity entropy space. So,
sorry, Cristina, the two border lines are something analytical or just you got to this?
I'm not sure if there is an analytical expression, but I'm sure you can calculate it numerically. I mean, there is this function, the entropy is the complexity is a function of the entropy, and you can calculate which are the possible values for a given value of the entropy, which are the possible values of. So the system can be it cannot be more complex than this, and it cannot be less complex than this. But I'm not sure if there's an analytical expression or it's just a numerical calculation.
Because most yes. This is pattern.
So the key question, in my opinion, is how to define this probability distribution that fully describes your system. So you don't want to lose any information. You need to use a probability if you want to be able to describe the complex system. You need to use a probability distribution that describes that system. So I'm going to talk to the second part of the introduction, which is this method of ordinal patterns and symbolic dynamics. Suppose you have this time series that comes from a certain system, and of course you can describe the system with a probability distribution just based by the simple histogram of values. Or you can do a binary representation. I will put an example in a minute in which you change this sequence into a sequence of zeros and ones and calculate the probability of the zeros and ones. Or you can go to Fourier space or wavelet form. But all these methods do not take into account the order in which the values appear in this time sequence. So the sequence of events is lost if you use this type of probability distribution. Let me, before describing the method that I'm going to employ, give you an example of how important it is in order to obtain a meaningful result to use the right probability distribution. Let's consider the logistic map. This is an old paper. You use the SIG complexity measure, which was also something mentioned at lunch today, in the previous seminar, which is based on compressing the information. You obtain this type of diagram for the complexity of the logistic map. You can also do a different type of analysis and consider just binary representation. So the variable is 0, 1, depending on the variable of the map. And then you can see that you get a completely different result. You get to the point in which fully developed chaos has zero complexity. And these plots are actually representing different ways of defining the complexity, as I explained you before, depending on which distance you choose and which entropy you choose. But basically, you can say that a regular and a completely chaotic both have complexity 0, which is actually bad because it's not the same. A chaotic regime should have some degree of complexity, of course. It's not purely random. So, how to define this probability distribution? And the method I think it has some advantages, has some problems too, is this ordinal patterns. So suppose you have this sequence of values, just as an example, and you choose to take words which have 2 letters or 2 numbers. No? So you can represent this as a 1 and a 2. Because, why is that? Because what you're looking is at the order of events, and then you see if the next value is higher or lower than your present one. So for instance, 9 will be higher than 7. So you get another 1, 2, and then here the same, but then you get a different word. You get 2, 1, and then 1, 2, and then 2, 1. And so you can define the probability distribution in this way. The probability of the pattern 1, 2 is 4, 6. The probability of the pattern 2, 1 is 2, 6. Of course, this is not very elegant. You can go to larger. If you want to find some correlations, some structure, you need to take longer sequences, of course. No? So you can say, well, here these 3 values I ordered in the sequence 1, 2, 3. This one's the same, but here is a different sequence because the smallest one is the one that's on the 3rd position, and then the next to small is the 9, which is in the 1st position, and then the last one is in the second position. So you get the pattern 3, 1, 2, and so on. So here you have more possibilities. You have 3 patterns that appear, but you have a total of 6 possibilities. 3 of them are not present, and are usually referred to as forbidden patterns if you have a large statistic enough. But of course, to describe a system employing this method, you need to go to large enough words, and for large enough words, then the number of possible patterns increase, and then you need to have a long time sequence to make sure that you have enough data to distribute into the different possibilities. But you can describe the system employing this way, and going back to the logistic map, here you can see that employing this Brandt and Popper method of ordinal patterns, you get a complexity that does not vanishes at 4, which as it did employing the other other complexity. Here the problem was not the complexity measure, but the discretization of the system. So they find that the probability distribution, the binary representation was obviously not good as compared to these ordinal patterns, in which what you do is take into account the order in which the different elements appear in the sequence. Actually, what we do...
Sorry, Cristina, I think I'm not understanding very well something. For you, the goal is that your complexity indicator, takes an intermediate value between, in the case in which you have a purely periodic, then you have something like 0 or maybe or anyhow small value. It's also small value or 0. Let's say white noise, and it's high value. It's a maximum when it's chaotic. So in this plot, when you have R going to 4 is isomorphous to the 10 map. So it's noisy, let's say. So should be, in some, this simple it should be smaller than, I don't know, 3.9.
Yes. It should be something like this.
Yeah.
You should expect a maximum.
Yeah.
But it shouldn't go to 0.
Yeah. Okay.
Okay. So I agree with you. I'm not that happy with this increase.
Yeah.
I would expect this to go down.
Yeah, right.
I agree.
Yeah.
I agree. I fully agree. I guess if you try with a different type of, I think you might be lucky to have that if you change the definition of your entropy.
Which did you use then?
Sally's entropy could help, but I don't know. No, and let me tell you that those are Osvaldo's. I'm just presenting Osvaldo's work here. I'm not part of this work.
This one doesn't go to 0, right?
Sorry?
The one on the left. The one doesn't go to 0.
No.
But it should go down somewhere.
But it should go down.
Should go down.
Is this something I can use? Pues no sé. Bueno, actually,
what is the number of values we use in these ordinal patterns? How many?
This one is done with a dimension equal to 6, which requires a large data, because if you have 6 dimensions, then the number of words is very high. And if you have a certain number of words, it's very high the sequence of data that you need.
And also the ordinal patterns. I'm not so familiar with the concept, and I have the impression this is a quite theoretical concept, because as soon as you have any practical data, since you don't at all take into consideration whether the step is large or small, you emphasize and amplify the influence of noise in your ordinal patterns a lot. So even if your original time series had only little noise, the effect that you have on your ordinal patterns will be even stronger. So how far does it work as soon as you have little noise in your...
That's an excellent question, because that's the main advantage of this method. What you do is compare whether the next value is higher or lower. Okay?
But it could be just tiny bit higher, tiny bit lower, which could be induced by noise, or it could be significant from the dynamics.
Exactly. But let me tell you that the actual gap is not important. The only important thing is the evolution, right? And of course, there is this important issue also of the sampling. Because if you sample very small separated values, of course the noise, you get completely different results. That's why I'm presenting values results on the logistic map, because the sample is not the problem. The sample, the values are well separated. And what I'm going to present now, which are time intervals, is not the value that is affected by the noise. But yes, this method has an advantage of doesn't care about that if it goes up a lot or just a little bit.
I was just.
And that's a drawback
considering
too.
huge
That's a problem.
disadvantage. Yeah, okay.
Because it doesn't distinguish between a long jump or a very small jump. You only care to know whether if it's longer than if your next step, if it's longer or shorter than your present step. It's an advantage and it is not at the same time.
How does the result depend on D?
I'm going to show that in a bit. At the moment, this is quite robust. Another thing I wanted to mention is that we are also interested, I don't have time to talk about it, about delay-induced complexity. Complexity not induced by noise, but complexity induced by delay. And we started working on a very simple case, which is the delay logistic map. We hoped it wasn't going to be a simple case, but it turned out to be very complicated. And it turned out that you can classify delay-induced patterns, delay-induced forbidden patterns. It was quite fun. But the extrapolation from discrete time to continuous time has a problem that Ngo was pointing out, and I think that's a key problem, that you need to be careful with your sampling, basically, if you don't want the noise to interfere too much. So let me just show the first part of the talk, which are the results on noise-induced complexity and order. And as I said, I was going to talk about the driving bistable system or an excitable model. And let me start with the simplest case, which is the bistable system plus a sub-threshold signal plus noise, which is a standard for stochastic resonance. The noise is a simple Gaussian noise. And I'm just showing you things that you for sure already know. What's the behavior when you change the noise strength, but keep this modulation frequency constant, or what happens when you change the frequency keeping the noise constant. You can see immediately that there is some region of noise or region of frequency in which there is enhanced regularity, right? You can see that the system here follows the input. This is a sub-threshold signal, so without the noise nothing happens. These are noise-induced jumps. And for a good level of the noise, then you have this synchronization phenomena with the sub-threshold signal. So what you usually do is characterize this in terms of either frequency analysis, analyzing the strengths of the frequency peak on describing this oscillation, or you can also analyze in terms of histogram of residence times distributions. You get this type of behavior, and you can, for instance, plot the maximum of the first peak, and you will have a maximum peak at a certain level of the noise, which means there's a large probability of jumping regularly, and people consider that a signature of noise-induced order, right? So what we did was consider the system, but try a different approach. Consider consecutive resident time intervals. So the time spent in one of the wells before the system jumps to the other. And we just compare the length of these intervals without worrying about the value of this. Just if the next one is longer than the previous one or not, and taking sequences of, I'm just showing some results for a vector equal to D, and you can see that there is a maximum complexity, which is the red line, which is accompanied by a minimum entropy, which is the blue line, and this occurs for a certain level of noise. And if we take the same data, but we just mix it randomly, and then do the analysis again, which is the empty symbols, you don't see any resonance. So here what we're seeing is that on the jumps, in the simple place of this stable system plus noise plus signal, there are some correlations in these jumps. Okay? It's actually not too difficult to understand where do these correlations come, and it is basically a fact of depends. There might be a correlation of the next jump depending on which way I come into the well. So this wouldn't be present on a pure bistable model. These are what we think is product of the intra-well dynamics. The way you approach to a well might be have some effect on how long are you going to stay there and where are you going to go next.
Cristina, sorry, I don't see why the complexity is maximum there. I understand that the entropy is minimum because you're almost in a periodic regime, but why the complexity is high?
Well, because basically, in principle, in this case, the complexity is almost symmetric to the entropy.
Yeah.
So basically, it's enough to consider the entropy. The complexity does the same, but we also at very high values of the entropy. You can see it's almost 1, and the complexity is very small. It's also almost 0. It's not a first order effect. I'm talking about something that is hard to detect because we are considered just a random system plus noise. Okay, so it's very, very random. Why the complexity goes up? My theory is that one. I mean, you are far from regular oscillations, and it's very far from completely random. You are in between, and that's by the definition of your complexity, that's what it has to do. It has to do a pixel. Well, the same thing you see when you keep the frequency, you keep the noise fixed and change the frequency, you see the same thing. There is a change in the entropy, there is a change in the complexity, and there is some structure there. At certain frequencies you have some maximum complexity which is accompanied by a minimum, relative minimum of the entropy. And again, if you mix your data and do the analysis again, you realize that these are arise because there are time correlations in the channels. For certain values, the time you're going to stay in one well depends on how you get in. How do you get in the well? We went a bit further and we consider the simple excitable system, closed noise. This is well-known effect of coherence resonance. You add a certain amount of noise and you have these regular spikes. You put too much noise, the signal is too noisy, and you put very little noise, the spikes are very sporadic, right? And then you can quantify this by the normalized inter-spike intervals, and this is also old paper. You have a minimum of the the variance, and you have a maximum of the correlation current signature in this coherence resonant phenomenon. What we did was basically the same. We applied the method, but to consecutive inter-spike intervals, analyzing then the sequences of intervals between consecutive spikes for different values of the parameters, and we found again this type of resonant behavior, which is characterized by minimum entropy accompanied by maximum complexity. So let me now say that we also did some collaboration with people in Terrassa. We also did some experiments at work. Let me describe a little bit very fast the system. Most of you perhaps already heard of it, just in case. What we consider is a semiconductor laser with optical feedback from an external cavity. This laser, under certain conditions, the intensity of the laser displays this type of behavior. It randomly drops to 0 and recovers gradually, and this is actually the filter dynamics. If you have, as you have now, a very nice oscilloscope, you can see the pulses, the fast pulsating intensity. These dynamics occur near the laser threshold. And interesting enough, in this system, it has been proven that you have these two phenomena that I just talked about. So you can find coherence resonance and stochastic resonance by adding a certain amount of noise. So it's expected that we're going to have it, but in Terrassa we don't have the possibility of controlling the noise. But the important thing is also proven this resonant behavior just deterministically, in the sense that changing the injection current of the laser. By tuning the injection current of the laser, you go from these well-defined dropouts to this kind of completely random regime that is usually referred to as coherence collapse. This is a work again by Ingo and co-workers. And if you plot the variance of the interspike intervals, you have this type of, again, minimum, which shows that there is some region of well-defined regularity in these dropouts. Again, in this case, it's slightly different because the dropouts are not induced by noise, but we're talking about induced by reflection from a external mirror. It's a bit also more complicated because there is regions in which what you have is actually a coexistence. You have intervals of LFF, and then you have a long interval in which you don't have any LFF. The system stays in a fixed point. You can model this with usual Lango-Hayashi model, which has done a very deep analysis of this type of behavior, and how much noise you need to expel the system out of the fixed point. But this coexistence means that there are very short intervals that can be followed by a long one. And that the method that we are trying to apply is perhaps not the best. Because, as I said, compares the relative value, but not exactly the value. So it doesn't detect these long intervals. So these are experimental time series obtained in Terrassa, different current. We see the time interval between consecutive dropouts following a logarithmic dependence from injection. This is also well known. And if you plot this value of the normalized standard deviation, you have this type of one experiment did not show the coexistence, but other one you show. You can see here large deviations in the variance, and this is due to the these trains of dropouts that can be all the fact they stop and then they come back again. So we did the analysis as unexpected. Both things happened what we expected, in the sense that we saw this minimum entropy at a certain point accompanied by a maximum of the complexity, but at the same time we don't see with this method what I was just explaining before of what happens when you have small intervals and large intervals that results in a deviation, large value of the standard deviation, which is not detected by this method. So I'm just going to the last part of the talk. We're probably in about 3 minutes. I just want to present some work in progress, and I want to discuss what networks have to do with climate. In principle, what do you do? How do you define a complex network in the climate? Here is there's some people that has been working on this for quite a long time. Let me explain you briefly how this type of plot is built. First, you can consider different type of field over the Earth. We have worked, for reasons I'm explaining in a minute, with the surface air. This is we have data that is in a regular grid all over the world over a certain number of years per month, and then you can consider that a pair of points are connected. If, again, talking in terms of the meeting large, if the matrix that defines the distance somehow, you can consider that they connected if they are above a certain threshold. The plot that I just showed has a threshold 0.5 for the cross-correlation coefficient. And then you need to take into account that not all the nodes have the same area, so you correct that, you consider the area-weighted connectivity, and that's what we just saw. This plot is basically this area-weighted connectivity. what do? You calculate the cross-correlation coefficient between any two pair of points. If it's larger, on absolute value, larger than 0.5, you consider them connected, and then you take into account that this point is connected to that one, but that point can be geographically small or geographically large. So you correct it.
Are you considering the delay, the time delay?
No, no delay. No, zero lag.
But the geography imposes some delay, right?
I can leave that for a little bit later.
Okay.
Okay? So, let me show you some couple of years ago by the same group describing, you can analyze years that correspond to El Niño, and you can analyze years corresponding to La Niña, and you can see that there's obvious different networks. You can give a lot of meteorological interpretation for this. And obviously we want to go further. Some people has already done that, of course, have considered the fact that the cross-correlation coefficient is a linear measure, and then we can compare linear and non-linear using something more sophisticated, which is the mutual information, for instance. What do? You employ this mutual information, and you basically get the same network as the linear measure, cross-correlation. This is a comparison of the non-linear and the linear measure if you choose the threshold such that the density of links is the same. Okay? So you can define two positions in the Earth are connected with a certain, if the cross correlation is not just 0.5 as the first plot I show you, but adjust this value such that you end up with a network that has a certain edge density. The edge density is the number of links over the total possible number of links. So for instance, I'm just showing results published last year. These people, by choosing, you can see these green areas, by considering this threshold for the mutual information, this threshold, they end up with networks that are very similar.
Cristina, what does it mean red in these plots? And there is a large cross correlation between 2 points in red?
What we're plotting is the area weighted connectivity. Let me
the
go
number of links that area has.
This plot is done assuming that 2 points are connected if they...
and this is the number of links that
this is the area weighted connectivity, which is the fraction of the total global area at which 1 point is connected. For instance, the Ecuador, if you consider that this is connected to almost all, and that's why it's very red. While other areas, they don't have any links or not many links, and they are...
So Antarctica, nobody cares.
Exactly. It would be proportional to the number of links.
Yeah.
In a
So Antarctica is not linked to anything.
the number of links, but it has to be corrected because the geographical area is not the same for all the nodes. Okay? But it's the number of links.
But this does not assume a directionality in the links.
No. It's mutual. It's cross. You can see it's cross correlation or mutual information. Both are symmetric. Okay? Just that one is linear and the other is not linear. But if you choose a threshold such that the density is the same, the density of links is the same, more or less they are distributed the same. Okay? So there's no big change by going. You can say, oh yes, you see much more, but this is pretty much the same. Here it shows you the regions. We are choosing the threshold high enough, so there is a very low edge density. Okay? Of course, it all depends where you put the threshold. If you put it at 0, everybody is connected with everybody. Okay? And of course, they do a very serious study on statistical significance on why you put this value and we just believe all this group and we just take this value and work forward. And what we did and what we're still doing, and this is work in progress, we have this, this is done in Uruguay. We have data for these years, which is not the same years as the previous work, so I'm just going to compare because it's slightly different years. And the data comes from the same place. Let me just very briefly explain to you that, of course, we don't have data in all the grid, in all the world, for every month. So what you do is run a sophisticated program and you feed it with the data that you have at the place you have at the time. So in this way you restrict the solution to a realistical solution where you have the data and to a possible solution where you don't have it. This can be considered experimental or theoretical data depending on which side of the spectrum you are. Okay? Some people say this is experimental because it's a sophisticated model but it's fit with all the experimental data that we have. But some of the data that I'm using are not actually observations but are, come from what is called the reanalysis. On the reanalysis, of course, depends which model you employ. So it's not, our results are similar, very similar, but not exactly the same. I don't want to enter into details. This is just too technical, but let me tell you that we have a large amount of data, and we have to be careful with the poles, for instance, because, of course, there's just a single point. We need to take them into account. Never mind about this. So this is actually our simulation, our work with our data, and just to show you with what I have shown you before, it's not exactly the same, but it's at least quite well. Visions that are relevant more or less are be well. If you consider the mutual information is the same, it's not exactly the same because the data is not the same and the reanalysis is not the same, but it's consistent with previous work. And obviously, the next step is quite obvious. What we're going to employ is the patterns. We're going to employ symbolic dynamics. So let me show you, just to put them together, that there's no change in which method, in which the network that you obtain if you define the threshold such that the number of links is the same. Well, these are more technical part. So what I'm going to do is apply these patterns, these ordinal patterns, to define the probability distributions that I'm going to put in that I'm going to use to calculate the mutual information. So now the mutual information is not just an histogram of the temperature values, but I choose as a word like before, and I look if the temperature next month is higher or is lower than the temperature this month, and I get a pattern, and then I compare the pattern here with the pattern somewhere else. Of course, I cannot use a word too long because I don't have enough data, right? Because to employ this method, you need, if you go to d values large enough, you need to have a long time series, which we don't. So,
you're using the delay 1 year instead of, you have said 1 month, or is 1 year?
That's the important thing. That's the important thing. What I'm comparing here is consecutive years. So I look at the temperature anomalies now, and next year, and the next year and so on, and compare the pattern in this place with the pattern in Montevideo. Okay? And you see the same, pretty much the structure is the same. Okay? So you can see the comparison. Of course, the threshold has to be completely different, right? Because the entropy is not in the same range of values. Obviously, it depends on the size of the discretization, etc. But it's not something that you would say, well. And if you consider different sizes, comparing 3 consecutive years, or 4 consecutive years, or 5 consecutive years, it's quite robust. It changes, of course, and as I said, this is work in progress. We still need to interpret this, but it's no surprise This is again showing you that there is, when there is high cross correlation, there is a region in which you have high mutual information, and of course it depends, the shape of this plot depends on which way you define these probability distributions. But here is what I think is something interesting, or at least we're thinking about it, is what happens if instead of comparing consecutive years, you choose consecutive months. And of course the pattern you get completely different. It looks like the equator that used to have a lot of links, has no links. And pretty much we are trying to interpret this type of results. But now, as I said, it's work in progress. What's the point? We are trying to say, well, what's the point of comparing without a lag time? Obviously, because if you're comparing the weather in North Hemisphere with Montevideo, Uruguay, you need to do a lag time of 6 months, correct? Obviously, but then is the point of the equator. What do you do with the points in the equator? So we're trying to consider that type of situation, trying to see if we can to find how to implement the lag time if you're going to do this type of comparison. But let me just summarize and try to remind you. What we're plotting is the area-weighted connectivity, which is proportional to the number of links. There's a link if the mutual information is larger than a certain threshold. The mutual information is the usual mutual information, but the probability distribution is defined in terms of ordinal patterns, and the threshold is defined such that in all cases we have a fixed edge density. In this case, we choose this value just to compare with previous work, but that's also something that we're looking forward to explore. And just to conclude, I have tried to convince you that the Shannon entropy and the complexity can detect and also can quantify some subtle signatures of resonant behavior that can arise in very simple systems by evaluation of a parameter or noise. That the success of this method is based mainly on having a good probability distribution that takes into account the time order in a sequence of events, the fact that the events occur with a certain order in time, and we have applied this methodology to various systems, as I said, the driving bistable system, the Excitable model, the laser, the pulse in the intensity of the laser, and the temperature anomalies. Thank you for your attention.
May I ask a provocative question?
Interpretation meteorological, no, please.
No, about the general motivation of the complexity method. You motivated showing that certainly you want to be able to detect complexity as not being completely ordered and not being completely disordered. Mm-hmm. And what I'm wondering is, why making life so difficult? It would only really make sense if you're able to distinguish systems in where these intermediate structures originate really from complex origin, and not, for example, from a periodic process on which you add spatial or temporal noise, where you would just have additive noise. Only if you can distinguish these two cases, you would go beyond what you could get with simple correlation measures, right? For example, finding that stochastic resonance has more order than if you have lower or higher noise is a trivial way to find out. You wouldn't need the complexity measure. So, do you have examples? That's the main question, where you would be able to say, I can distinguish that a periodic process where I have additive noise, I can distinguish as not being complex, while a process where this disorder or this intermediate disorder comes from a self-organized process is being recognized as complex.
I don't know if I'm going to be able to answer your question, but I'll try. I put an example, I can try to go back to that, distinguishing noise from chaos. And it was different type of noises, and with this entropy complexity diagram you can distinguish, but you can also say it's noise.
Take a periodic process, put a bit of additive noise on it, and you will get probably more.
It depends on which noise you add. You can distinguish different noises. You can distinguish different type of noises. If you have color noise, you can distinguish the color of the noise by these entropy complexity diagrams. They are really, I don't know how to use them because again I'm working with other people, and the person that is in charge of the complexity is Osvaldo. So he could probably give you a better answer than me. But I just put you also that example of characterizing brain dynamics, distinguishing noise sick from healthy brains by these complexity entropy diagrams. It's one tool more. We are in the nonlinear business, and this is one more tool to play. But it's also useful. In my opinion, it's useful.
So the question is, when do I use it?
Sorry?
When do I use it?
Well,
instead of the other measures.
Well, I think they are complementary. That's what I try to show with the LFF example. With the LFX example, clearly there are some things that are not detected by this. This coexistence is not detected, which you can just easily find by calculating the standard deviation. But then you won't know the fact that there are some correlations in these intervals. You might think it's total. The next event is totally independent of the previous, and it's not a Markovian at all. And this is quite surprised. I was actually quite worried about this because in stochastic resonance you're not supposed to have this. In stochastic resonance you're having a Markovian process. Well, how can you explain this memory? Or in the excitable system, it doesn't make any sense. In principle, it's a Markovian system, there's no memory, and the next event is completely independent of the present event. And I'm just showing you that's not exactly true. It's not exactly true. In certain situations, the length of the next step depends on your past. I mean, I found this quite difficult to accept. Really, I did a lot of tests to make sure. And I understand now that actually on the bistable system it's easier to understand. It's not exactly two-state model. There is this intra-well dynamics, and then depending on which way you come into the well, it will depend how long will you stay before jumping again. But in principle, I think it's quite actually surprising. There's no memory in these systems. It's not delay. It's just white noise. Why would there be some memory?
I've learned from quantum information that when you try to define a measure or something like this, then the bigger difficulty is finding what is the most in this case. What is the most complex in this case could be. And then you define also operations which are supposed to live intact. So exactly the same, the measure should be constant and there's some transformation. So for example, what would be the most complex?
Well, I have to say, I'm not the expert on this, but I think I'm not using the most complex. I'm convinced about that, because the most complex, perhaps Raul will know better than me on the Salis, for instance. Salis entropy would be even more complex than this, because that's not extensive.
No, but not the measure, but you're trying to measure how complex is a behavior.
I'm just
and
trying
then you
to
are giving a
define
number of how complex it is. I'm telling you that typically the biggest problem is finding what is the extreme of the ruler.
Yeah, but we have things normalized. Because we normalize, we can say that it goes between 0 and 1.
But you are putting first a measure, for example, Salis entropy, this complexity measure and so on, and this defines this maximum in the middle. But this maximum in the middle
it doesn't have to be in the middle, and there can be no maximum. It depends on which you're using. And I'm not claiming that this one is better or worse. It probably depends on which system. I show you the example of the logistic map. Depending on how you define a probability distribution and what type of complexity measure you use, you can end up with a 0 or with something that grows. Depends. I don't know if I'm answering your question.
What I'm saying is that you first define what should be the point which has maximum complexity, and then you find the measure.
No, here is, no, we don't. Here we exclude processes that are not complex. those ones have to satisfy complexity equal to 0. But then something in between depends. It might be or it might not be complex depending on which complexity measure you use, which entropy, which distance, and how do you define your periodic distribution.
Okay.
Yes. Regarding the complexity entropy diagram, then you have some processes like chaotic processes and stochastic processes, and they belong to different parts in this diagram, right? So now imagine you have an experimental time series, and you calculate the complexity and the entropy, and you have this dot here in the middle of the diagram. And do you have information about the process? I mean,
no, I agree with that. A dot in the middle of the diagram is not very useful. I agree. But
I mean, does the diagram tell you something about whether it is purely chaotic or just stochastic, or?
If you have any information about the system, it might give you some information about the noise. I mean, or as I said, it might give you a possibility to distinguish between two situations. But just one dot in the middle of the diagram, I agree with you, doesn't say much.
Because the title of the paper was distinguishing noise from
chaos. I think in principle these kind of things are useful to distinguish two situations, but not by itself. Just in the end, it's kind of like the Lyapunov exponent. You calculate and you end up a number. The Lyapunov exponent is -24.
Yeah, but you know, if it's negative, it's not.
Yeah. Well, here you can say, well, it's positive and it gives you this number, and if you normalize well, the maximum is 1. So you know whether you are in middle complexity, high complexity, low complexity. But that's all. It's not very useful in my opinion.
But the Lyapunov exponent gives you a number that has a precise meaning.
Yeah,
I mean, it means that if you put at a given place two trajectories from here, well, you know how much is the time they will take to go away.
No, I agree.
So it is a quantification of something that can be tested in situ. In some places, and if you don't like to support other trajectory, you can also support finite time Lyapunov exponents or whatever which also is measured. So that's something to be tested precisely in that. I guess that this is more difficult. It's a kind of general measure that it does not have a counter-intuitive part which is intuitive and counter part which is intuitive.
Okay, any other comment or question?
If not, Cristina needs a rest. So.
Puede ser que esté mal, ¿eh?
Yo no tenía,